look at some applications of what we learned so far. So though we termed the last few classes as we are looking at motion of particles in the fluid, okay, and that naturally occurs when you're talking about settling of particles in a fluid, right? So we looked at something called as a falling ball viscometer, right? Okay, uh, in which you basically had a container, right, a capillary, and you take a particle of known properties, okay, that means known diameter and known density, okay, and if you have a way of measuring what is the density of the fluid that you're working with, right, and then if you have a way of calculating or measuring what is the terminal velocity, that is the maximum possible velocity that the particle attains, okay, in a given external field, okay, and if you're working in under the influence of gravity, right, right, so therefore what I can do is I know that this ut I can relate, it goes as g dp square into rho p minus rho divided by 18 mu, right? That's for your Stokes regime, okay. If and if you look at the formula for settling velocities, uh, only in the Stokes regime there's a dependence of the settling velocity on the viscosity, right? If you look at the Newton's regime, your settling velocity doesn't depend on the viscosity of the fluid, okay. Therefore what they do, they use particles of appropriate dimension, okay, so that the settling falls in the in the Stokes settling regime, that is your Reynolds number is less than 1, okay, as long as you ensure that I can basically exploit the Stokes settling principle, and if I'm working with particles of well defined sizes and densities and fluids of known density, I can actually calculate what is the viscosity, right? That's one of the applications that we've looked at already so far. Separation of so settling principles are kind of explored a lot in particle separation, okay. If you have, like, say, particles of one size or multiple size, okay, one type or multiple types, okay, you could have a case where I have particles of same type, okay, of a given density but different sizes, or I could have a case where I have a mixture of particles, particle 1, 2, 3 of different materials. It could be like, say, glass beads plus polymer beads, for example, okay. So if you have particles of different sizes and different properties, okay, so you can actually exploit these things. So we'll talk a little bit about some of these things in the remainder of the class. So before I go further looking at separation of particles, I just want to give you a little bit of heads up with some places where sedimentation is kind of really useful. I don't know how many of you have heard of something called the ESR, which is called as a erythrocyte sedimentation rate. Have you heard of this term? No? Yes, somebody says yes. Where have you heard? It's a test that is done when somebody goes for a diagnosis, right? What they do is they take a small amount of blood sample, okay, and one of the tests that they do is this sedimentation measurements, okay. The experiment basically involves taking blood in a small capillary. You just let it sediment, okay, and looking at the sedimentation rate, you can actually tell something about whether the blood belongs to a male or a female, somebody who's young or old, okay. Plus it also is one of the nice ways of measuring or finding out if there's something called the inflammation, okay. Whenever somebody has some disease, okay, there's going to be inflammation, right? So basically this sedimentation rate measurements are simpler measurements for kind of as a first tool for diagnosis, okay. And so in that context, people do. So I again picked up some image from Wikipedia, wherein these are basically capillaries which are filled with blood and made to sediment for some period of time, and you can clearly see that there's an interface between the clear capillary and the the brown or reddish mark. From finding out what is that interface, I can say something about sedimentation, right? If I had a homogeneous, so maybe just to tell you. So initially the blood was, say in this case, the blood was filled up to this level. Okay, after some time, you can clearly see all the whatever particles that you had in blood, okay, RBCs and other stuff, that has now the mark is here. Therefore this is a, a clear plasma. There's no particles there, okay, and all the particles are now kind of concentrated here, right? So basically by measuring this interface, okay, between the clear fluid and the samples where there are blood particles, I can actually measure the sedimentation rates. Okay, this is what is typically done, and depending upon, as I said, disease conditions and the type of person you're dealing with, you'll have different values. Okay, so this is one applications where you actually can actually use exactly the same equations that you used. Okay, you should, if you know the dimensions of the blood, if you know the viscosity of the blood, you can actually also calculate what is the settling rate. I'm going to talk about an application that kind of people have. So in the class so far, I only talked about mostly sedimentation under the influence of gravity, right? Of course, we did mention that you can use external force in the form of centrifugal forces to do sedimentation as well, right? So there's a nice concept called paperfuge. Okay, any thoughts what it could be? Okay, this actually, it comes from a paper that appeared in 2017 in a journal called Nature Biomedical Engineering. It's published by a group in Stanford, which is headed by Manu Prakash. Okay, and there's one person who is Saad Bamla, who's involved with this work. He's an IITM undergrad. He finished his BTech few years ago, finished his PhD in Stanford. Okay, so the title of the paper is Hand-Powered Ultra Low Cost Paper Centrifuge. Okay, the reason why they call it as paperfuge is because it's a centrifuge and we can actually make it out of paper, right? So I just have a video from okay, let me just try and show you a video of this. I'm sure all of you have played with this at some point. Okay, so there's a lot of study before this kind of. Okay, let me just. I have some uh, slides from the paper. Uh, so an interesting aspect of this is, if you noticed, so when you're pulling it, right, there's a linear motion that you're applying. Okay, that kind of translates into a rotation, right? And what they did is they looked at so basically what is happening when you do this, there's a winding and unwinding, right? And at some point, if you clearly see that the spinning disc actually stops, right, when there's a complete winding, right? So what they've done is they've taken different designs. Okay, they did experiments with a lot of different designs of these discs. Okay, and they used high speed camera to measure, okay, what is the rotation speed. and as it was mentioned in the video, you can actually reach speeds which are as high as 125,000 RPM. Okay, and that can actually translate into a gravitational force of the order of 25,000 to 30,000 G. Okay, that which is really huge. Okay, and you have a plot here. Okay, that is measuring phi max, which is the maximum rotation speed as a function of disk diameter, right? It turns out that if you make it smaller, you rotate it faster, right? If you really want to go to very high G's, right? Therefore, you would be using a smaller diameter disk, and if this diameter becomes larger, your speed is going to go down. Okay, so depending upon what kind of speeds you want to generate, you can actually exploit the fact that the maximum phi max varies with the disk speed. And this is again the device that was mentioned. What you have here is that's a kind of a hollow tube, okay, in which you can put a capillary with any sample that you have, right? And all you have to do is close it and then spin it. Okay, this is a demonstration of what basically happens. Okay, that's the fraction of RBCs in the blood. Okay, that is that the y-axis go from 0 to 1, right? And your x-axis is the time. Okay, and of course, as the clear fluid kind of starts appearing, I can also measure what is the plasma volume, right? When the fraction of the RBCs in the blood is like 1 here, your plasma volume is 0, right? Because it's a homogeneous fluid here. Okay, at some point somewhere here you start seeing some small volume of clear fluid. That's when a small volume of the plasma appears here. So basically it's a simple demonstration of how the separation happens. Okay, in terms of monitoring what is the fraction of RBCs in the blood and the fraction on the plasma volume. And these are the microscopy images taken at different location. And the stop region where it's only plasma, there is absolutely no cells. Okay, that means all the cells that were there have kind of settled, and that's the interface here. Okay, between the clear fluid and the settled RBCs, and that's your image where you have a lot of RBCs. Okay, so it's a very simple tool which is kind of kind of developed, which is again exploits the fact that you can basically use very high external force, right? External force of very high magnitude to really separate stuff. Okay. Any questions? Yeah. So okay, do you understand the plots? Okay, the plots is basically you have when you have the blood particles, RBCs kind of homogeneously dispersed in the entire fluid, then RBC fraction is 1. Okay, the moment a small amount of, you can also think about this in terms of the volume ratio as well, right? I have the entire volume of the fluid, okay, and of course I don't have any fluid without the particle. So in that case, my the reference is 1. Okay, therefore in the next stage what I see is I have a very small fraction of the clear fluid that is formed. Okay, that volume divided by the total volume of the blood that I had taken, that gives you some fraction. That is basically a measure of how much of sedimentation has occurred, right? Now on the right, what you have is basically microscopy images. Okay, the fact that I clearly see visually there's a difference for sure, okay, between when I started and and at some instant during your separation. And other way of confirming this would be just to take out some small sample from different locations and you do microscopy. Okay, and if I do microscopy from the small sample that I take from the top, I don't see anything, right? Okay, however, if I take some sample from the bottom, okay, and if I do microscopy, it's not a very high magnification image here, but what you see is, can you see some small circle like things here, right? These are basically RBCs, okay, red blood cells, which have a typical dimension of about 8 micrometer. Okay, the scale ball here is about 10 micrometer. Okay, so therefore you'll see typically, I mean, the objects that you see are sub 10 micrometer dimension. Okay, this is just to say that the visual observation that you see here is, is kind of confirmed by doing some microscopy measurement. That's all. Yeah. Oh, so basically, I mean, no, this is a, see what they have done. So you're talking about, see these, you see these large error bars, right? Okay, these are actually done over several measurements. Okay, there could be some fluctuations because of, conditions as well, of the person, whose blood has been drawn. There could be some other fluctuations. So basically, but the point is, that you basically reach some kind of a plateau, right? If you wait for sufficiently long time, okay, you see that, you absolutely, that means at that point all these RBCs are kind of packed. Okay, there's no more space for them to even, sediment further, if you, even if you continue to do prolonged, centrifugation. So, okay, so so I've kind of talked about elytration in the last class. Maybe, I was trying to draw a picture myself, so it wasn't clear. So elytration is again a technique that is typically used for separation of particles. Okay, so if you have a mixture of particles, like say, just to give an example, let's say I have a mixture which is like say 1 micrometer, 10 micrometer, and 100 micrometer particles. Okay. Now, elytration is actually is a reverse of sedimentation. Okay. Now, if you look at the schematic here, what you have is there's a feed stream. Okay, that feed stream basically carries the mixture of particles that are that want to be separated. Okay, so I have a mixture of different sizes. You could think about maybe feed stream consisting of say 1 micron, 10 micron, and 100 micrometer particle that enters the feed, and at the bottom you have a fluid stream. Okay, and with this fluid stream, what I can do is I can basically maintain a particular flow rate, right? I have a control over what is the flow rate with which I can send the fluid stream in, right? Because I have control over the fluid stream, volumetric flow rate, I also have control over their velocity, right? Now what happens, these particles are going to come down because of gravity. Okay, now what I can do is I can actually manipulate the fluid stream velocity such that it to maintain a particular value, such that, for example, let's say that 1 micrometer I have a particle and 10 micrometer particle. I can calculate their settling velocities, right? Under gravity, what is the settling velocity that they're going to have. Now, if I have information about that, if I want to separate out, okay, if I want to separate out 100 micrometer particles from this mixture, what I do is I maintain a fluid stream velocity such that the velocity of the fluid stream is larger than the settling velocity of 1 micrometer particle and the 10 micrometer particle, such that when the fluid stream goes up, okay, the smaller particles basically come out. Okay, 1 and 10 micrometer particles, they come out of the the container, and the larger ones basically sediment out. Okay, therefore what you do is I can actually manipulate, okay, the fluid stream velocity, and I can actually by design I can actually find out, okay, or I can say, hey, I only want 1 micrometer to come out. Okay, I can do that. I want a mixture of 1 and 10 to come out. So basically that's how the typically separation is done in the case of elytration. Okay, so what you do is the particles with the terminal velocities less than the upward velocity of the fluid are basically carried out, carried along with the fluid. Okay, that's what happens in a elytration. Okay, and this typically is used if you have particles of different sizes but of same density present in a given mixture. Okay.